Thank you, Mia. Our next speaker will be talking about, solar system formation. Ms. Bianca Pina, please come to the podium. This is Professor Jenny Weiss's.
How's everyone doing today? Good? It's the last day of school. Okay, so my name is Bianca Pina, and I'll be talking to you today about solar system formation. Let's see if I can do this up here. Perfect. Okay, so before we get into solar system formation, I kind of want to give you guys a little bit of an overview of the universe that we live in. So Earth and our solar system is just one of millions of other solar systems in our Milky Way galaxy. Now our galaxy is about 100,000 light years in diameter. So what does that mean? Well, in 1 second, light can travel just under 300,000 kilometers. That means in 1 second, light can travel around Earth in about 7.5 times around Earth in just 1 second. So it's massive. And the Milky Way galaxy is just one galaxy in 100 billion other galaxies in just our observable universe. Now, does anybody know what I mean by observable universe? No? Well, see, the universe, in its 4.6 billion years of existence, the light from the other end of it has not even had enough time to reach us. So that is just what we can see, but it is still constantly growing. So it kind of makes us all feel a little small, doesn't it? Even our solar system. But it's not. Solar system formation is so essential because that's how we're all here today. Now, there's a couple different theories on how our solar system formed. We've got the capture theory, the protoplanet theory, the modern Laplacian theory, and then, of course, the solar nebula theory. Now, the most widely accepted by scientists is the solar nebula theory, which is what I will be going over today. Now, it is important to note that this is just a theory, it is not law. There are still a couple things wrong with the theory, but for the most part, it works, which is why this is the most widely accepted. So the solar nebula theory was first introduced by Emanuel Swedenborg in 1734. However, it wasn't for another couple decades that Immanuel Kant took the theory, revised it further, and actually published it in his works. So all of this, everything that we are, starts from one molecular cloud, calmly existing in space. It is a cold, dark cloud made up of atomic gases and cosmic dust. Now, in order for solar system formation to even begin, the cloud needs to begin contraction. So contraction is when gravity at the center of the cloud causes it to collapse in on itself. See, but not every molecular cloud out there has the ability for contraction. James Jean, who was a British physicist, came up with Jean's criterion. So he essentially said that this molecular cloud must be of a certain mass, and that certain mass must be of a particular diameter. Which makes sense if you think about it. It's got to be so big to where gravity can spark out of nothing inside of this cloud to begin the entire process. So once a molecular cloud has the ability for contraction, and it meets Jean's criterion, there's a couple different ways for contraction to begin. The first of which is through a blast of a nearby supernova. A supernova is the explosion of a star. So when a star explodes, it sends shock waves and debris into the galaxy. Now, if the molecular cloud is close enough, these shock waves will push the cloud inward, beginning contraction. We actually have some evidence that strongly suggests that our own universe actually became from a supernova. It's kind of interesting. A couple other different ways contraction can begin. Just the natural spiral of our galaxy slowly having influence on the cloud, it can just begin naturally that way. And lastly, it can begin through density waves in our galaxy. galaxy, there are parts that are denser than others. So if the cloud finds its way into one of these density waves, that could easily kickstart contraction. So contraction has begun. So what happens is this cloud starts to condense and starts to rotate counterclockwise and starts flattening out like a disk. It starts to pull in on itself. Kind of think about if you've ever made pizza and you take the dough and you spit it in the air, what happens? It starts from a ball, but then it starts to flatten out like a disk. Now at the center of this solar nebula cloud starting to contract, we have the formation of the star. Before the actual birth of the star, it's actually called a protostar, so the beginning stages of it. So this protostar happening at the center of this molecular cloud is a hot ball of hydrogen gas, and it is condensing in on itself and slowly starting to form. Now, it is important to know that with these nebular clouds, they don't always form solar systems. Sometimes just a star is formed. Sometimes you get a binary star system which is formed, but they don't always make solar systems. So back to this protostar, as it is forming, as it is condensing, what's happening is the gravity from that star is pulling itself inward. It's contracting in on itself. But that's building pressure. What does pressure want to do? It wants to go out. So the star is always in constant battle with itself, contracting in and wanting to push itself out. Now, while this is happening, at the exact same time, we have the beginning stages of planets starting to form, which we call planetesimals. Now, as you can see from this picture here, you see a lot of matter, a lot of rock surrounding this protosun. What happens is, as it's rotating around this, the rock starts to all kind of gather in on itself, and it begins to accrete, and thus you have the planets starting to form. Now, in the inner regions of this, where it's a lot hotter, you can see how it's yellow and orange. That is where you get the rockier planets that start to form. Now, this is because the rockier planets, those elements have a higher melting point. So gaseous planets cannot form in these regions because it's too hot for gas to form. The molecules are too excited, they can't come together. That's why in our own solar system, you see the terrestrial planets closer to the sun, and then you see your Jovian gassier planets in the colder regions farther from the sun. So as these planets are starting to form, they're rotating around the protostar. They go through a process called sweeping. So if you look at the first picture here, you see all of this matter around the protostar. And then slowly, as it all kind of clashes into together, it starts to come together, it starts to settle into its orbit. That's how you eventually, you get the size and composition of your planets. Now, during this sweeping process, during all of this, you also have chemical differentiation happening. So the planets are spinning, and they're spinning fast. Well, if you've ever done spin art as a kid, you know that when you put paint on a spinning paper, it splatters outwards. Well, the same concept kind of applies to this. What happens is your heavier elements, like your metal oxides, those sink into the planet because the lighter elements, like your silicates, those get thrown to the outside of the planet as it's spinning, which is why you see these different layers in a lot of planets. So again, this is all happening at the same time. The protostar is in battle with itself. The planets are forming, they're going around. Now, the star, because it is battling gravity and pressure, that begins to create a lot of heat. This is actually called the Kelvin-Helmholtz contraction. So essentially, the heat is building because of all this gravity and pressure. Well, as the heat continues to build, as soon as it gets up to about 10 million degrees Kelvin, it ignites, and nuclear fusion begins within the star. Now, nuclear fusion is when the hydrogen atoms get so hot, they actually fuse with themselves, and they make a completely new element. Does anybody know what that is? I want to guess?
Helium.
Helium. Yep, I heard it. Yeah, so it makes a new element. So nuclear fusion is the process of the hydrogen atoms fusing and turning into helium atoms. Now, when that happens, that is considered the birth of the star, and it is born. Then what happens? At that moment of ignition, it blows an interstellar wind across the new solar system. And this blows away any extra dust or cosmic gas that hasn't been accreted up by any of the planets. And that's how you get that nice, perfectly formed solar system at the end of it. Now, this entire process takes millions and millions of years. Again, just depending on the size of the original molecular cloud. I mean, these clouds can be anywhere from just 1 or 2 light years across to hundreds of light years across in diameter. So they definitely vary in size. Taking a look at a timeline of our own personal star, you can kind of see where we're at here. So in another few billion years, Earth is going to be too hot to support life. So this is why space exploration and proper funding for space exploration is so essential to the survival of mankind. And that is the end of my presentation. Any questions? No questions? You have questions for everybody else? Any good questions? Oh, yes. Hi.
What were the flaws?
What was the what?
What were the flaws?
Gosh, they were little flaws about like the angle of some of the planets in relation to the sun. They're pretty minimal, but again, it's not a perfect system just because we don't have a lot to go off of. This whole process does take millions of years, so it's, you know, with our lifespans, it's almost impossible to observe this from start to finish. Yes, hi.
So, assuming that humanity lasts that long, is the sun heating up the Earth, is that the biggest cosmic danger to the Earth in its immediate?
Immediately, no. I mean, we still have another few billion years before our sun turns into a red giant and expands out into the inner solar system. I mean, realistically, we'll probably all kill each other off before this even happens. I'd say probably the most dangerous would be like an asteroid coming from interstellar space coming into our solar system. Solar flares. I know in 2012 we had a really scary miss with the solar flare at that time. So there's a lot of different ways.